All right, so I want to take a couple minutes here to talk about some of the factoring from the zeros worksheet yesterday. And the one thing with factoring is we've been doing it for a long time. So back in first semester of Algebra 2, you do a ton of factoring. It's coming back again now, and it really doesn't go away for a long time. So we're going to use it for the rest of Chapter 3. It's going to come up in the next chapter, Chapter 4. So you want to make sure that you're starting to feel pretty good about factoring. And if it's something you feel like you're kind of weak on, you want to make sure you work at it, you ask questions, you kind of get it under control. If it was something you weren't great at in first semester, you need to really put in the time and the effort to kind of make sure that you're understanding what's going on. So in terms of factoring, if you're trying to factor a problem, which is what we're trying to do on every single one of these, we're trying to factor it in order to find the zeros. The first step in any factoring problem is try to pull out a GCF. If you can do that, you should always do that first. So in this problem, there is a GCF. There's at least a y squared in each of these. So what I did is I went ahead and I pulled a y squared out of both of these. When I did that, I was left with just a y here and just a 9 there. And at that point, this problem is completely factored. Now, when I say completely factored, what I mean is you have everything down to either a linear factor like this, where it's just like y to the first, or if you've pulled out like a single variable and it's like a y squared, an x to the third, or something like that, nothing here can be broken down or factored any further. So lastly, once it's factored, you just say what the zeros are. So in other words, what numbers would make each of these parts equal 0? So this part, if y was negative 9, would make it a 0, because negative 9 plus 9 is 0. And then for this part, sort of obvious, it would just be 0, because if you put a 0 into here, this is going to become 0, times whatever this is, stays 0. Now, I did note that the 0 does have multiplicity too, because it appears twice. There's technically y times y, so there are two zeros at 0. The reason why that's important is we know going into the problem there has to be 3 solutions. We talked about it in the notes. Whatever the degree is, that's how many answers you're going to get, how many solutions. So 1, 2, 3, because this one appears twice. All right, so if we keep moving on here, like I said, I look for a GCF. This one doesn't have one. There's nothing I can divide out of both of these. This one is one of our most common kind of little shortcut rules, which is called a difference of squares. It's something squared minus something squared. In other words, there's a 0p in the middle here. And this is one of these where you would take your factors of c, so factors of negative 36 that have to add to 0, which are going to be 6 and negative 6. But every time you see one of these that has this format, I think there might be another one later on too, like this one's going to be the same kind of thing, number 11. Anything that's a something squared minus something squared is going to always factor to plus and minus whatever the root of this is. So p plus 6 and p minus 6. And therefore the zeros are negative 6 and positive 6, because that's what would make each of those parts equal 0. Number 3 is a typical quadratic factoring problem. So no GCFs to pull out, but a is 1. And when a is 1, all we have to do is the factors of c. So in this case, c is 20. And you want to find the factors of 20 that add to 9. So numbers like 1 and 20 are factors of 20, but that would add to 21, so it's too big. So what ends up working here is 4 and 5. Because 4 and 5 multiply to give me the 20, and they add to give me the 9. And so therefore, those are going to be the two parts that make up the two factors, x plus 5, x plus 4. And then the zeros are negative 5 and negative 4. That's what we then give for our solution. 4 is exactly like this, except you pull a GCF out first. I pulled a 2 out of everything, boom. And then I was left with a problem where I could just do, okay, my c is 16, and I found factors of 16 that add to negative 8, which I used negative 4 and negative 4. So that's how I got to here. And then this is another good example of multiplicity. The 0 for this is 4, and the 0 for this is 4. So the 4 appears twice. We'd say it has a multiplicity of 2. And so technically it only has one solution, but that same solution appears twice. Therefore, meets the condition of needing to have 2 solutions. Number 5, I think this is the only one on here like this that is a not equal to 1 factoring. So again, we check for a GCF. This one doesn't have one. But when a is not 1 is when we have to use our AC, or our grouping style of factoring. So I multiplied a and c together and got negative 60. And then I found factors of negative 60 that added to negative 7. So I used negative 12 and 5. And then this is the one that you cannot just say, okay, it's not just going to be a minus 12 and a plus 5, because we have to make this 6 appear. So the move for this is you rewrite the middle term with these two numbers. You group the first two and the last two together, and you pull out each of their GCFs. After you pull their GCFs out, you should have matching parts in the parentheses. And so the last move from here is These two parts make the first factor, so 6a plus 5 is one factor, and a minus 2 is the other factor. From there, what are my zeros? Positive 2 would make that part 0, and a negative 5, 6 would make this part equal 0. So coming up with what number would make this factor equal 0. So kind of a tough one there. Like I said, I think that's the only one. This is definitely less common factoring, but it is, a thing nonetheless. Number 6 didn't factor at all. There's no GCF. It's a cubic, and we don't have any rules for factoring cubics yet. So at this point, all we did was graph it. Same thing we did in the notes today. Yesterday, I guess technically. If I graph this one actually just crossed in 3 spots. I know it's supposed to have 3 zeros, so I just looked these up on the graph or looked these up on the table, and they were at 8, -1, and 1. And that's actually a nice little strategy to remember, that when you graph these, the zeros are the solutions. So the same things you're getting from your factored forms here as we're getting the zeros. So in this case, this one is just graph it and see the solutions, because we don't know how to factor it yet. And again, that's what it says right here. If the problem can't be factored, graph it to find the real solutions, and then do the other steps, which we'll get to later on if you have to. All right, this one, GCF out, normal, factors of -3 that add to -2 style of factoring. If you could do the ones before, 7's just like those ones. Same exact thing with 8. 8's another, pull out the GCF, and then factor the remaining quadratic. I did lie, sorry. Number 9, you factor out the GCF of x, and then this is another AC style of factoring. So this is like that one we did earlier, where we had to find factors of AC and rewrite the middle term. So there's another example of the same thing, plus having a GCF. So in the end of this one, you have the x out front, which gives you a 0 at 0. And then you have the 2 factors that you come up with from the factoring, which gave me the other 2 solutions, the 6 and the 1/4. Okay, here's the difference. These next 2 are both difference of squares problems. This one's an easy difference of squares. So you're just going to be, it's w plus 8 and w minus 8, because those will multiply to give you the -64. So negative and positive 8 are your zeros. This one is a little bit tougher difference of squares, because it's actually, it's a 4th power. So what we break it down to first is, this is going to be x squared times x squared. This is going to be 4 times -4. So we get x squared plus 4 and x squared minus 4. Those then can each be individually factored too. This is just another difference of squares. So it's going to factor to x plus 2 and x minus 2. And this one's a sum of squares. We talked about this the other day, and a lot in first semester, but sum of squares factors to imaginary factors. So this is a good example of where you have difference and sum of squares and showing what the difference of those two are. How are they like? How are they the same? Basically, difference of squares, you always get real factors. Sum of squares, you always get imaginary factors. Okay. And this one here, 12, is another pull out the GCF and then factor the remaining quadratic with factors of 11 that add to 12. In this case, another good example of multiplicity, the 0 right here appears 3 times. So I said 0 has a multiplicity of 3. Negative 11 makes that part equal 0, and negative 1 makes that part equal 0. So there are 5 solutions there. The one of them just happens to appear 3 times. Okay, and then the last 3 problems are all like what we did in the notes, the day this was assigned. And so the process on these, we don't know how to factor any of these yet. We haven't learned anything for factoring a quadratic. So like it says in the instructions up top there, the first step is we graph it. And for every single one of these, when you graph it, it crosses 1 time, which is good and bad. It means that's one of the solutions. So when this one crossed at -4, -4 is for sure one of my zeros. Okay, I can write that down right away. But my other 2 are then probably imaginary, meaning they're off the grid. We have to go find them. So I took the 1 0 I knew, and I divided it out of this polynomial using synthetic division. So I followed my synthetic division process to work this down now to a quadratic. And this quadratic is the one I'm trying to find the answers to, because I already know this solution. I'm trying to find the remaining 2 solutions from this. I took it and I put it in the quadratic formula because I knew I was heading towards imaginary solutions because I only saw the one right here. So I put it in the quadratic formula and I simplified it out. Now with each of these, I try to show kind of all the steps as you're working through it. And again, when you're writing these, because they're coming in pairs, it's going to be plus and minus. These are my 2 imaginaries and my 1 real solution. And you'll notice for every single one of these, you can look at the PDF of the key too, but you got the 1 real solution, the 2 imaginaries, the 1 real, the 2 imaginaries. So all 3 of those problems at the end all kind of follow that same process that we learned today. So hopefully that's helpful for you, and we'll keep on rolling.